Welcome. In this session, we're going to learn the charging concept of an inductor. Let's start. So, how the inductor charges? What is the behavior of the inductor current as we connect a source to this inductor? For this concept, what we're going to do, we're going to take an example of an RL network. Suppose we have an RL network. And let's suppose we connect this RL network to a source Vs at t equal to 0, means we are applying a source to this RL network at t equal to 0. And let's see the behavior of the current that flows through this inductor. So our goal is to study this inductor current when we connect the source. So before for t less or equal to 0, means what is the current or inductor current in short? For t equal to 0, we are going to assume it is equal to 0 for t less or equal to 0. All right, so that is the assumption. Means that initially the inductor is not charged to anything. All right, so now let's see what will be the behavior of the this current after we connect this. So we can draw the equivalent circuit. We can draw it like this. So this is the inductor. This is the source voltage. This is R. And let's study I of t. What's I of t? All right. So let's use KVL. Let's apply KVL to obtain the expression of this I of t. So what we'll have? We have V of S. You can say minus times V of S plus I times R of t plus what is the voltage drop across this inductor? L di by dt. So L dit by dt, and that will be equal to 0. Or we can write it like this: dit by dt plus R by L I of t is equal to Vs of by L. So this, after rearranging the terms, what we have done, we have taken this to the right hand side. It will be Vs, and dividing both sides by L, we obtain this expression. Now, if we compare this equation with this expression, dy t by dt plus py is equal to q. Again, we are going to see that this equation is a linear differential equation. So this is a linear differential equation where P is equal to R by L and Q is equal to Vs by L. Vs is a constant voltage. All right. So this is the linear differential equation. So how do we solve a linear differential equation? We solve it by using the concept of integrating factor. What will be the integrating factor here? E to the power of integral P dt. P is equal to, P is R by L, so it will be R by L dt. R by L is a constant, so we can say e to the power of R by L t. What is the integration of dt? It is t. All right, so multiplying with this integrating factor to this expression on both sides, what we'll get? We'll get e to the power of R by L t d by dt of I of t plus e to the power of R by L t R by L I of t is equal to e to the power of R by L t Vs by L. So after multiplying this expression with e to the power of R by this state, now we can write the left hand side like this. We can say this is d by dt of e to the power of R by L t I of t. and that's equal to R by L T Vs divided by L. All right. Now, what we have done, we have combined these two terms in a single term like this, and using the product rule of differentiation, you will get it back. Okay. All right. So integrating both sides, what we'll get d by dt of e to the power of R by Lt I of t, integrating both sides dt, then integrating this R by L T Vs divided by L plus some constant of integration. All right. So now you can see dt cancels with dt, this cancels with this. What we are left with, R by e to the power of R by Lt I of t is equal to, now Vs is a constant, L is a constant, so we can take it out. So this is Vs by L e to the power of integration of e to the power of R by Lt dt plus some constant of integration. So we can write it as R e to the power of R by Lt I of t is equal to Vs by L e to, what's the integration of this term? It is simply e to the power of R by Lt divided by R by L plus some constant of integration. So this L and this L cancels. What we are left with, you can say R e to the power of R by Lt I of t is equal to Vs by R e to the power of R by Lt plus some constant of integration. So what we need to do, we need to determine I of t. So dividing both sides by I of t, what we will get? So dividing both sides by e to the power of RL by t, what we'll get? I of t will be equal to Vs by R plus constant k R by Lt, but minus when you divide this by e to the power of this, right? So this is the current. So now we need to evaluate the value of k. How do we do that? By substituting the value of t. Put t equal to 0, we say I of 0 is equal to Vs by R plus k e to the power of 0. E to the power of 0 will be 1, so it is simply this. So what's I of 0? I of 0, we have assumed this is equal to 0, means there is no current flowing in the inductor at t equal to 0, because we are just connecting this inductor to this switch, and we are going to assume that I of t is 0 for t equal to 0. All right. So what will be k? K will be 0, simply Vs by R. So substituting back it here in this expression, what we obtain, we say I of t is equal to, sorry, this will be minus Vs divided by R minus Vs divided by R e to the power of minus t by, sorry, this is wrong. So this is R by L t. All right, so this is the expression that we obtain of I. So we can write it like this. I of t is equal to Vs by R 1 minus e to the power of R by Lt by taking Vs by R common. All right, so this is the current flowing that is valid for t greater or equal to 0. And for t less than 0, R equal to 0, this is equal to 0 for t less than 0. So we can combine these two statements. We can combine these two statements in a single statement by writing like it does. So I of t will be simply Vs by R 1 minus e to the power of R by Lt u of t. How? Because u of t is 0 for t less than 0, that will give you this part. U of t is equal to 1 for t greater or equal to 0, that will give you this part. So this expression is the general expression which is valid for t less than 0 and t greater than 0. All right. So this is the current flowing through the inductor. Now, what's the behavior of this, or how does the plot look like? The plot looks like this. If we plot this, the plot looks like this. Means what is the behavior of I versus t. If you plot it, then it looks like this. At t equal to 0, the current is 0. You can check it. At t equal to 0, the current is 0. As t increases, the current increases. As t increases, the current also increases. So current starts increasing and it reaches to the final value Vs by R. And for t less than 0, the current is 0. That's what we have assumed. And finally, it reaches to this value. Now, at t equal to infinity, this term will be 0. You can check at t equal to infinity, this term will be 0. So the final current will be equal to Vs by R. So the final value of this I of t will be simply Vs by R here. All right. So this is the behavior of this current, inductor current, when we connect it to a battery, which is initially relaxed or which is not charged initially, means when no current flows through this inductor. All right. Now, how much time it takes to reach this value, means how much time it takes to reach this value, that is entirely dependent upon the parameters of the circuit, that's R and L. All right, remember this thing. We'll discuss it once we discuss the concept of time constant. We'll discuss it there. So how much time it takes to reach to this Vs by R, it is entirely dependent upon this R and L parameters. All right. Now in the next session, what we'll do, we'll learn the concept of this discharging of an inductor. All right, let me stop here.